In this lecture, we're going to continue to look at time series, univariate time series, and this will be a shorter lecture so that this slot we can dedicate more time to exercises. But we're going to extend a bit what we saw in the previous lecture. So in the previous lecture, we looked at simple moving averages and correlation and autocorrelation as tools to analyze time series. Now we're going to look at more sophisticated moving averages, so weighted linear moving average and exponential moving average. And also we're going to look at a different way of analyzing periodic processes in our time series. So instead of autocorrelation, we're going to do a spectral analysis. We're going to decompose the time series into frequency components. And to do that, we're going to use the Fourier Transform. Now, I'm not going to go into details about this. The mathematics of Fourier Transforms and this kind of analysis are outside the scope of the course, but I'll just give you a brief overview on how to use this in practice to try to find regular processes that occur during the time and that you can see in your time series. So we saw in the previous lecture how to do a centered simple moving average. So we take a window, we average the points in that window, and we assign that average to the point in the center of the window. So this way, our moving average takes into account not only the past points, but also the future points and falls in between that group. So this is what we saw in the last lecture. We have this radius, which is how many points around the central one we want to compute our average for, and then we compute the mean for that point using that neighborhood. But we also return, besides returning that moving average, we also return the x values for the points corresponding to each value on the moving average. The reason for this is that depending on the window size, we are going to leave out some points at the end, some points at the beginning, and so if we need to align the plot, it's convenient that this function returns both the x and the y values. Then in the exercises, I gave you as an exercise to implement the version of the simple moving average that is more used in financial analysis. Since in this case we are interested especially in the last points in our data series, we don't want to have a moving average that leaves out some points at the end, and it makes more sense to have a moving average that only looks back, that only looks to the past. So in this case, we are computing for each point the mean, the simple mean between all the points on that window, ending on the point to which we're going to correspond the moving average. So for some given point in this index, we're going to assign the moving average value to that point by averaging over all the points until up to this one. Now there was a small typo in the solution for this exercise. I forgot to put the +1 there, because if you don't do that, then you're cutting your interval before reaching the last point, and you're not taking the last point into consideration. So don't omit that +1 there. But this is the same idea as the centered simple moving average. We are just taking a simple average, but in this case, the window is not centered on the point for which we're computing the moving average, but it ends on that point. So that way we can compute this moving average all the way to the end of our time series. So in this case, we could compute the simple moving average for example, the prices, the Bitcoin prices. In this case, our simple moving average is this financial variant. So I called it the financial moving average just to distinguish from the other one. Of course, when you're writing your own functions, you don't need to use these names. Use whatever is appropriate in the context of the function you're working on. But just to revisit what we did in the last session, we're going to load the file. In this case, this is a matrix with each column having the price of one crypto coin during around September 13. for 24 hours, and we can plot the values of this data and the moving average that we compute here. So this is the plot of the values on the first column of index 0, and all the rows using dots, and this is what gives us here all these dots for Bitcoin, which is the one in the first column. And then we compute a moving average, and we plot. So here we compute a moving average with a given window, and we plot that one as a line. But I want to compare moving averages computed with different windows. So I created here a list of the window sizes, 5, 10, 20, and 50. And for each window size, I do this plot inside the loop. So I repeat this for each window size. I do it for window size 5, window size 10, and so on. Since I'm plotting several series, PyPlot automatically changes the colors. For this label, I'm going to add, I'm not going to put a label on the dots here, so this will not appear on the legend, but I'm adding a label to each moving average where I include the window. And if you want to do formatted strings in Python 3, this is the most convenient way. If you precede the string delimiter by an F, you are telling the interpreter this is a formatted string. And in this case, everything that falls inside these curly brackets is interpreted by the interpreter as if you were actually giving that instruction, and the value is placed in the string. So since this window inside curly brackets is a variable here, what the interpreter will do is put the value of the variable inside this curly bracket. Note that this can be any expression. You can do computations, call a function, do whatever you want. So this is a very powerful way of formatting strings in Python 3. It works similarly to the format method for strings, but it's often more convenient. So this way I'm doing this loop, and then I plot the chart here with the different windows. And as you can see, as we increase the window, we start looking further back in time. So points that are further back in time are more influential on the moving average here. So you see, with the small window, we climb up this set of points quickly, but with a very large window of 50, for example, we finish here because we're still averaging over a lot of points here in the back. So this is for the simple moving average ending with the window ending on the point for which we are computing the average. Another way of computing a moving average that is often used in time series analysis is to assign different weights to the different points further back in time. In theory, you could do this with any combination of weights, as long as they added up to 1 in total after scaling, so that you have a weighted average. But in general, in financial analysis, it's usually a linear progression. So it's something like this. The last point counts the most, then the one before last counts a bit less, and so on, until we reach the end of the window. So basically, point T has weight W, point T minus 1 has weight W minus 1, and so on until point T minus W. This should be small here below, so it should be like this. It only counts for 1, and then we rescale everything to the sum of all these weights, which is can be computed by this formula, which is the area of this triangle here. So that the whole thing scales up to a total weight of 1 distributed over the different points. So we can implement this easily like this. This is the linear moving average with this decreasing weight for the past points. We can compute the weights by using this array range function. So a range from NumPy. This works similarly to the range that you use for iterations, but instead of returning an iterator, it returns a NumPy array. For example, a range 10 gives you values from 0 to 9, so 10 number integers from 0 to 9. So here we are going to compute the weights for our window, and this will give us, for example, if we have a window of 15, it will give us 15 values starting at 0 and ending at 14. But actually we want 15 values starting at 1 and ending at 15, so to get the proper weights. So we add 1 to all of these, and we have the correct weights. Now the scaling factor here, we need to divide by the total sum of all these weights, which we can compute either by calling the sum function, but that would be a bit inefficient because it will have to sum all of these values. But we can also use this formula, which is the area of this triangle here. And so this is the scaling factor. We need to divide by this or multiply by 1 over this to get the weighted average. Okay, so now we start with similarly to the simple moving average. We cannot start from the first point. Note that we need to start at the end of this window, otherwise we don't have the points further back to compute this weighted average. So we start at the end of the window, and we now compute, and we compute the value for each moving average by multiplying the values in the interval for that window, multiplying that by the weights. So if you do this with NumPy, you have two arrays that have the same number of values. For example, the last 15 values times the 15 weights. And what NumPy does is return an array with the same size, but doing the multiplications element by element. So the first element of this interval here will be multiplied by the first weight, the second one by the second, and so on. So we are doing this multiplication here, and then we divide by the scaling factor, or we in this case I did the scaling factor 1 over the area of the triangle, so I do a multiplication, but you can also, if you want, to put the scaling factor with this value and then divide at the end. The result is the same. So we are computing here the moving average values and appending to that list and returning the array, exactly like we did the ones before, only in this case it's not a simple moving average, but it's weighted, giving more weight to the last points and less weight to the first points. So now we can do again the same plot. I omitted some parts like the figure and so on, those things that are always the same. In this case I just changed a bit here the label. And now you can see the effect here. So if we compare with the simple moving average, we can see that the weighted moving average for the same window size, since it gives more weight to the final points, in this case it's climbing a bit more than the simple moving average. So you can choose depending on what you want to focus on. With this weighted moving average, you still consider the window, but now the points at the end of the window weigh more than the points at the beginning of the window. Another way of doing this is, instead of using a simple a linear moving average, we can use an exponential curve. Or if you use a very low value, it can approximate and looks a lot like a constant one, because you get the first values here. So note that the scale of these plots are a bit different, but you can control this curve by adjusting the alpha parameters here. And the idea is that we are computing a moving average with weights similar to what we did here, but the weights are decaying exponentially. So we have alpha here, but then we have alpha times 1 minus alpha for the point before, and then alpha times the square of 1 minus alpha. And so this term, since alpha is between 0 and 1, this is below 1, so we are decreasing exponentially the weight of each point as we go farther back in time. You can control the shape of the curve with the alpha, but the decrease will be exponential. In practice, we don't need to do this like this infinite series, or computing overall our data series for each point. We can do this recursively. So we can start with our exponential moving average for the first point to be equal to the point itself. This is not really an exponential moving average, but we don't have any points before this one, so would be an approximation. And then for each point at time t, we compute the exponential moving average at that point by multiplying alpha with the value that we have in our time series at time t, and adding 1 minus alpha times the exponential moving average computed up to t minus 1. So since this will start nesting all these multiplications, 1 minus alpha, this will eventually do something like this. So if you do it for the next time step, the first value on your time series has already been multiplied twice by 1 minus alpha. When you go to the first point has been multiplied 3 times, and so on. So instead of having to repeat all these multiplications, we can go through our time series and just keep multiplying the 1 minus alpha times the previous result of the exponential moving average. Now, this one is a bit different from the others in that it doesn't have a window defined, because when you reach the end, you are actually taking into account all the points in your data series, although the first points have been multiplied so many times by this small value that they probably are now counting nothing or next to nothing. But we don't have a rigid window for the exponential moving average. However, if you set alpha equals to 2 times 2 divided by some w plus 1, this will give a set of weights that has the center of mass, so to speak, similar to a simple moving average with window w. So we can implement this with a function that, instead of asking for the alpha, which is a bit harder to estimate mentally, it asks for a window, and it works similarly to the simple moving average with a window, in the sense that it centers the weights on the same point. However, since this is an exponential decay, the actual shape will be different. Okay? But it allows us to write a function where we still receive a window as a parameter, and we can more easily calibrate this or compare this with the other moving averages. So receiving this window, we compute the alpha that corresponds to that window. We are not actually using a window. This is just a reference for computing the alpha. And then we are going to use all the x indexes. The x will be all the indexes of our values, because with the exponential moving average, we can compute the moving average for all the points in our time series. And now for each point in our time series, we start our moving average by just copying the first value. That will be the first moving average value. But then from the second onwards, we multiply the last moving average that we computed. So this is the last element on the y array, on the y list, multiplied by 1 minus alpha. And we add that to the value at time t, which is this one, multiplied by alpha. So this sum we append to y, and then when we go to the next one, this is the value that we're going to use here to multiply by 1 minus alpha, and we keep doing that all the way to the end of the array. This gives us values for all points, but note that at the beginning, when we start just by looking at one point, and then we start adding these terms. So before you reach some point where the tail is already vanishing, this is not quite stable yet. So for the first points, you have some value there, but it's not stable. It starts stabilizing as you go along the time series. So if we plot this is the example of the exponential moving average here, and you can then compare with the others. So this will actually be the first exercise, but as you can see, the idea is the same as the other ones. As you increase the window, you start increasing the weight of the previous points, but still you have this kind of of curve on the weights that you are assigning. So in general, it tends to be more heavily weighted towards the last points than the previous ones. So the first exercise that I would suggest you do, I'm going to update the PDF with more exercises, but first I would suggest that you try to implement these moving average functions just by looking first at the slides so that you have an idea, you understand the algorithm and so on, but then try not copying the code from the slides. Try to implement it by yourself, because if you can implement the functions, that means that you really understood how these moving averages are computed. And then you do this and you compare the three moving averages on the same plot. So you can choose a window and compare the three different ones using one of the time series. So you can use the Bitcoin prices, for example, too. But if you want, you can use the other time series that we used previously. Okay, so now let's move on a bit, extending this idea that we saw with autocorrelation, in that we can try to find some periodic events on our data. In this case, we're going to decompose our data into a set of frequencies. So you can imagine that if you add sine waves, for example, like this, I create here a set of 200 points. This lean space gives you a linear progression between two extremes. So in this case, 0 and pi multiplied by 4, so 4 pi. And this is the number of points in the vector. So here I just created 200 points going from 0 to 4 times pi, which is this axis here. But then what I do is I compute the sine value for each of these points, add 1/5 of the sine value multiplying these points by 2, so doubling the frequency, and then 1/2 of the sine with these points divided by 3, so I'm making the frequency lower, and then multiplied by 4 and so on. So if I add these, I get this curve here. So you see some higher frequency components, lower frequency components here as I'm adding these curves. So you can imagine that if we add an arbitrary number of this kind of curves, of waves, of different frequencies, we could, in theory, approximate any time series. So anyway, the data is changing, we can just add different curves with different weights, and by interference they would approximate our time series. So we can think of spectral analysis as doing this backwards, in reverse. So we start with some set of points, a time series here, and we try to decompose this back into the frequencies which could be used to generate that time series. So this is the idea of Fourier transform. This is basically what a Fourier transform does. I'm not going to go into details on the mathematics. This is a bit complex and outside the scope of the course, but it's easy to do if you have if you understand that what you get from the Fourier transform will be a decomposition in frequencies. So you are converting the time series from the time domain, where your axis is the time that is going by, and you are converting this into the frequency domain, where your x-axis will be each frequency of each wave that composes your time series. So in order to do this, you can use from the NumPy library, you have an FFT module for the fast Fourier transform, and then we can call the RFFT, which is the Fourier transform for real discrete data, not complex data, but real values. So this would be the Fourier transform of our time series. This y here is this time series, this curve that I plotted here. And if we want the power spectrum of this series, so the power spectrum is the variance contributed to the whole series by each frequency. As we decompose our time series into different frequencies, we can compute how much each frequency is computed to contributed to the variance of our data. And to do that, we take the absolute value of the Fourier transform and then the square. Now, this may seem a bit strange because if you square, you should not need the absolute value, but that would be true only for real values. In fact, the Fourier transform is a set of complex values, so we need to take the modules of those values before squaring in order to get the power spectrum. But we don't need to go into the details of that mathematical part. This is just, all you need is to use this to find periodic events, is to have this idea that you are changing from the time domain to the frequency domain, and then by squaring the modulus of these complex values that the Fourier transform gives you, you are looking at how much power each frequency contributes to your data series. The reason this is called power is that if you do this with the electromagnetic waves, then actually this variance is equivalent to power of the radiation there. So that's why this is called the power spectrum. Okay, so in this plot, what we can see is that we have a peak at a frequency of around 0.7 radians, more or less, and then one at a lower frequency of around maybe 0.15 radians. So these are the units that we are using here in this. So this is this would be the higher frequency. It's a bit below, between 1 and 2 radians of periods here. So remember, the periods of these oscillations is 1 over the frequency. So if we have a frequency of about 0.7, for example, the period should be about 1.4, and this is these oscillations here, which are a bit over 1 radian in periods. So we are capturing this higher frequency signal. And then we have this lower frequency signal here below these higher frequency waves, and that is the first peak we get here, which is at a low frequency. This xlim command here in PyPlot allows us to set the limits for the x-axis. So actually this goes all the way to 6. You can compute frequencies corresponding to 1/2 your to compute to be able to measure the power at some frequency with the Fourier transform, you need at least 2 points for that. So the higher frequencies you get here depends on the time step you have on your data. But in this case, we don't have such high frequencies. We have frequencies that are relatively low relative to the number of points that we have here. So we don't much care about that part of the axis. And this xlim will limit the x-axis here between 0 and 2. So this is 2 per radian. It's the maximum frequency we are getting here. So let's take a look at real data using this approach. This is the CO2 concentration in parts per million measured at the Hawaiian Observatory for the last 10 years. Each point corresponds to 1 week, and we can see this increase here, and we can see these oscillations which are caused by vegetation growth and decay in the northern hemisphere. So the Earth is a bit asymmetrical in that you have a lot more land mass in the north. So all the growth of trees and plants and so on during spring and summer will decrease CO2 in the air, but then when leaves start to fall in the autumn, it will produce more CO2 and inject more CO2 into the air. So this is the yearly oscillation, and then we have another signal here, which is this growth, which we cannot see actually where this ends. So this would be a very, very, very low frequency. And in fact, when we do, I'll show this first. When we plot the power spectrum, so we are taking the Fourier transform of this set of values here. So this CO2 is this series. When we do this, we plot the power spectrum over the frequency as a function of the frequency, and we can see that we have a very large peak here that drowns everything else. So basically, if you have a series that is not centered and has some trend, the very low frequencies will have a very large signal, because at frequency 0 this corresponds to the mean value for your data series, and then the first frequencies that you get, the very low frequencies, will be a function of these trends. In this case, since this was centered at 0, we did not see that effect, so we did not have a very large peak here in the beginning. So expect, if you do this fast Fourier transform, expect to find a large peak right at the beginning unless you center your data. Another thing that we can look into more detail now is how we can create this axis showing the frequency. So I was just talking about the frequency here. We can look at the frequencies here also in weeks. If we want to exclude this large peak from here, we can just set the limits on the y and x values. So this x limit is because we don't much care about very high frequencies, so we don't want to look at this part of the plot. And we also cut the y limit here, so we are not drowned by the signal coming from our data series having values that are far above 0. So it starts at 300 to up to 415, and also this large trend. This will give us those signals at very low frequencies, and we want to ignore them. But as you can see, we can find a peak here at the frequency of 0.02. So this means that the frequency is 0.02 per week, or if you invert that, the period will be about 50 weeks. So 50 weeks is 1 year, and this is what you can see here, these oscillations. Now, to plot the frequencies correctly, we need to compute them based on the time step that we have and the number of points that we have. The formula is not very complex, but it's more convenient to use this NumPy function, RFFT frac, which is, it gives you the frequency that corresponds to the x-axis you need when you do the Fourier transform for that time series. So what you need to add here to give to this function is just the number of points that you have and the time step at which you took the samples. So in this case, the time step is 1, because we are considering 1 week. Our time units is weeks, and we are considering 1 week at a time. So we get the frequency in 1 over weeks. This is the units for our frequency. In this case, we were using 200 points here to go from 0 to 4 times pi. So our degree step here, in this case in radians, will be the 4 times pi divided by 200. So each step is that number of radians that we're taking, and this gives us the correct frequency in 1 over radians. So doing this with these two functions from the FFT module, the RFFT and the RFFT frequency, you can easily create these plots. And if you set the limits accordingly, you can then look at those peaks. So very large peak here at low frequencies is caused by the mean and the trend of our series here. But then we can see a peak here at 0.02 per week. This is a frequency, so about 50 weeks of period, and this corresponds to this yearly oscillation that we can also see in the autocorrelation plot. So if you do the autocorrelation, you can also see these autocorrelation here. I did this for 100 of max lags, and you can also then see again autocorrelation at 2 weeks and at 2 years, 4 years, and so on. The difference is that when you do autocorrelation, you can find these correlations periodically, because you can imagine that if you shift these data 1 year, you will overlap these curves and you have a peak in the autocorrelation. But the same if you shift 2 years and 3 years and so on. So with the autocorrelation, you see these waves like this. With the spectral analysis, you can see a very strong peak at 1 year here. So this is the frequency corresponding to a period of 1 year. And then you see it on a slightly higher frequency. So this is one for corresponding to a shorter period of 6 months. And you can see the difference here. It's not this regular waves that you have here. In here, it's hard to see the 6 months correlation, but there seems to be some frequency there at 6 months, and then you don't see higher frequencies. Of course, when I speak frequency at 6 months, maybe I should be a bit more careful. I'm talking about the frequency that corresponds to a period of 6 months. So you have to invert this, because this is 1 per over week. Okay. So this is the idea for spectral analysis. You compute the Fourier transform so that you get a decomposition of your time series into frequencies. You compute the power spectrum from that, which is the modulus, and then there is a typo here, so it's missing this part, the square of the modulus. And then you use the x-axis, you can compute the frequency either manually or using this function. So this is more convenient, so that you know to which frequency each peak corresponds to. And then the trickier part here is the interpretation, because when you do autocorrelation, you're looking at the period, and you can easily see that there is a 50-week period or 52-week period here corresponding to a year. When you're looking at the power spectrum, you're looking at the frequency domain. So you need to work out how this corresponds if you want to think about the period. But it's not hard, it's just the period is 1 over the frequency and vice versa. But the spectral analysis is more sensitive to small contributions to different frequencies that you would not be able to detect easily by looking at the autocorrelation plot. Okay, so to sum up, we saw some more elaborate versions of the moving average, the linearly weighted and exponential moving average, and we saw a more powerful way of looking for periodic processes in our data series. So with the Fourier transform, we can extract the frequency of the different components that can be added up to create our data series. And then with the power spectrum, we can analyze the contribution of each of these components and get an idea of what kind of periodic processes are occurring there. So today I'm going to update the lecture notes with the exercises. And tomorrow we can take the slot, the tutorial slot, for you to actually start doing those exercises and see if you have questions and so on. So basically, your homework before tomorrow will be just to listen to this lecture, and by tonight I should be able to upload the exercises we're going to do tomorrow.